In this video, we're going to talk about some guidelines that can be used when choosing a segment size for your numerical model based on finite difference approximations. We're going to use that same example of an estuary to discuss some guidelines for choosing the size of segments. When using a numerical model based on finite difference approximations, the results you get are the concentration at discrete locations throughout your system, corresponding to the concentration at each segment. These concentrations are being used to estimate the concentration at the interface between segments and also to represent when there is a gradient or large change in concentration that exists between segments, so that segment size becomes quite important. Otherwise, you may be introducing errors into your solution. I already mentioned one guideline that can be used in choosing a segment size, and that is when looking at your system to break it up into sections where the hydrogeometric properties appear to be fairly constant. In the examples shown here, we have 4 segments defining this estuarine system. If we take a look at it, though, you might ask yourself, well, why don't we break it up into some smaller segments, right? In this section, this is really constant, the width in this section, and why don't we break it up even a little bit more like that? One of the things you want to keep in mind in choosing your segment size is that relates directly to the number of equations that are going to be solved, right? Because the transport equation then gets written for each and every one of the segments. One of the trade-offs with this is that you would need to know then or have data for each of these segments. Otherwise, you won't be able to solve your model. The other thing is the more equations you have, the longer it would take to solve it. Although with computers anymore, that isn't necessarily an issue unless you're dealing with very complex systems here. Another point to consider is what the size of adjacent segments should be. Remember, we're trying to model the concentration distribution through this estuary. And so if your segment sizes vary greatly from one segment to another, this could potentially cause a numerical instability in your solution. And so kind of a guideline that has been found is that when choosing segment sizes, you want to limit the difference in the segment size of adjacent segments such that from one segment to the next, the difference in segment sizes is no less than 50% of the adjacent segment. For instance, if this segment size is, let's say, 6 kilometers, we would want this adjacent one to be at least 3 kilometers or more in order to have to minimize introducing errors into our solution. There will be times when you're going to need to use finer segmentation in areas of your system in order to be able to capture significant changes in concentration. Whereas in other parts of the system, if you know that the concentration changes gradually, you may be able to get away with a coarser grid. And so applying this guideline becomes important in transitioning, particularly from a finer to coarser grid. One of those locations where you would expect a significant gradient to exist is at the point of discharge. Here you have whatever your levels are in your existing system, and then you're inputting some amount of the pollutant. And so some care should be spent in choosing what the size of the segment would be surrounding the point source itself, and then the segmentation in a way expanding out from that point, right, adjacent to the segment in which the your point source is going into. Moeller in 1976 developed some expressions that can be used for estimating what the length of the segment should be surrounding a point source. And he did this for advective and dispersive systems based on the dispersion number. So eta here is the dispersion number that we've already talked about. The expression, as you see, is in terms of the average velocity in your system, the reaction rate coefficient, obviously the dispersion number, but also this additional parameter, which represents, you can think of it as the type of error that you're going to simulate between the actual peak concentration in your system and the concentration you would get from your model. And so you tried to, that's why it's called the desired fractional relative error in that peak concentration. So you can set, in other words, what you want that to be. These equations are a starting point for choosing then the segment size surrounding the point source, and can then be used, right? Once you set that one, then you can choose the segment size adjacent to that particular segment based on the guideline that I gave you of no less than 50% in size. These are just some basic guidelines you can use in choosing the segment sizes for your system.